Assalamualaikum warahmatullahi wabarakatuh. So in this video, we are going to share with you on capacitance of three-phase line with unsymmetrical spacing. Our group consists of three members, which is Muhammad Adam Ashad bin Azmi, Muhammad Taufik bin Abdul Salam, and Muhammad Afiq Khairani bin Muhammad Zamri. Capacitance of a transmission line is the result of the potential difference between the conductors. It causes them to be charged in the same manner as the plates of a capacitor when there is a potential difference between them. The capacitance between the conductor is the charge per unit of potential difference. Capacitance between parallel conductors is a constant depending on the size and spacing of the conductors. For power lines less than about 80 kilometers long, the effect of capacitance is slight and is usually neglected. For longer lines of higher voltage, capacitance become increasingly important. So there are two types of the system, which is equilateral and unsymmetrical. So in this video, we are going to share with you on unsymmetrical spacing of three-phase line. When the distance between the three-phase line conductors are not the same, which is they are not spaced equally from each other, then it is said to be unsymmetrical spacing. Unsymmetrical spacing of overhead line conductors give rise to unequal voltage in the individual phases at the receiving end, even though the flow of current in each phases are same. This unequal voltage is due to difference in inductance of each phase conductor. Thus, it is very important to understand the inductance of three-phase overhead lines.
The effect of unsymmetry between the lines is small, and the calculations are carried out by considering transposition of lines. As seen in the figure, let x, y and z be the spacing between the conductor A, B and C respectively, and the r be the radius of each conductor. When phase A is in position 1, as shown in figure 1, and B in position 2, and C is in position 3, the equation is like VA1. Next, when phase A is in position 2, B in position 3 and C is in position 1, the equation is just like VA2. And lastly, when phase A is in position 3, B in position 1 and C is in position 2, the equation is just like VA3. Next, to calculate the average value of the voltage of the conductor A is such as VA equal to VA1 plus VA2 plus VA3 over by 3, and VA1 is defined as 1 divided by 6 pi epsilon naught times by Q1 ln 1 over R cube plus Q2 plus Q3 ln 1 over XYZ. At a balanced condition, which is Q1 plus Q2 plus Q3 equal to 0, and from this equation Q2 plus Q3 equal to minus Q1, and the value of VA equal to Q1 divided by 2 pi epsilon naught times by ln cube root of XYZ over by R. The capacitance of conductor A is given by CA equals to 2 pi epsilon naught divided by ln cube root of XYZ over R, and the value of CA equal to CB equal to Cc, which is 2 pi epsilon naught divided by ln cube root of xyz divided by r. So now I will continue the presentation. So I will discuss about the effect of unsymmetrical spacing of the three-phase line conductors. So the flux linkage of each phase conductors for unsymmetrical spacing are not same. This is due to the inductance of the three-phase conductor will be different. There will be unequal voltage drop in the three-phase even though the currents in phase conductors are balanced. Thus, the voltage at the receiving end will be same for the three-phase. Thus, the voltage at the receiving end will not be same for the three phases. To have equal voltage drop in phase conductors, we normally interchange the positions of conductors at equal interval along the line. Therefore, this interchange is known as transposition of line. That's all from us. Thank you.